How's it going, ladies and gentlemen? Mr. Ron here again, looking at 17.4 solubility equilibria. Alright, so first question is, which compound listed below has the greatest molar solubility in water? So we got to figure out how we're going to go from KSP to molar solubility. Alright, and it's different for different things. Let's take a look at a couple of examples. Let's look at the first one right away. So the KSP here is going to equal the concentration of the cadmium ion times concentration of the CO3 minus 2 ion, the carbonate ion. Now it's 1 to 1, so the exponents are 1 and 1. So they're going to be equal to each other in concentration if we're dissolving cadmium carbonate. So we're going to have essentially x times x. So the KSP is really going to be equal to x squared, where the x is the molar solubility. All right, so if we want to know the molar solubility, we just take the square root of the KSP for that, and we end up with x. Now for this one, cadmium carbonate, I'm going to make another chart here. I did that, and for that one I got 2.28 times 10 to the minus 6. Now the next one is a little different. And it's a little different because of how many ions it breaks up into. It's not 1 and 1, it's 1 and 2. So what we really have is KSP equals the cadmium ion times the OH ion, the hydroxide ion, squared. Now the question is, how do these two compare to each other? Well, if I get 1 cadmium, I'm going to get 2 hydroxide. Now what further complicates things is that 2 times the concentration is also squared. So when we square that, we end up getting 4x squared times x, and we end up with 4x cubed equals our KSP. So for the next one, if I want to get the molar solubility of cadmium hydroxide, I got to do, all right, well, KSP divided by 4, and then cubed root it, or 1/3 power, is going to equal my molar solubility. So when I do that, I get 1.84 times 10 to the minus 5. And CaF2 is just like that one. We're going to do the same process. We're going to get 2.14 times 10 to the minus 4. AGI is going to be like the first one, where it's x and x, so you just take the square root of KSP, and you get 9.11 times 10 to the minus, I'll put there 9. And ZnCO3 is going to be like the first one as well. You just need to take the square root of the KSP, and you get 3.74 times 10 to the minus 6. All right. So basically, you got to remember, first write the rule with the power, and then figure out, all right, well, this would be x, the molar solubility. You get 1 mole of cadmium from the cadmium carbonate or cadmium hydroxide, whatever you're looking at. And then, all right, well, hydroxide, if I'm looking at this one, I'm going to get 2 times that concentration. So it's 2x inside of that parentheses, and that's squared. All right, so that's kind of how you do those ones. All right, 2 says, what is the concentration of iodide ions in a saturated solution of lead 2 iodide? KSP is this. All right, so let's do a little figuring. The KSP for lead iodide, well, lead 2, Pb plus 2, iodide is going to be minus 1, so the formula is going to be Pb(I2). So the KSP is going to be concentration of Pb ion times concentration of the iodide ion squared. So we know the KSP, and we know, all right, well, if this is all I got, lead iodide, I'm going to get a certain amount of lead, and I'm going to get 2 times as much iodide. Now, in the KSP expression, that's going to get squared. So I'm going to get KSP equals x times 4x squared, or 4x cubed equals the KSP. So the first step is I've got to figure out, well, what is x? So I got to do a little algebra, and I get x equals KSP divided by 4 to the cube root, the 1/3 power. So for that, I'm going to solve. I'm going to get x equals 1.52 times 10 to the minus 3, but I'm not done yet. I found the molar solubility, but it's asking what is the concentration of iodide ions. Now, the iodide ions concentration is 2 times that of the molar concentration because you get 2 iodide ions for each lead iodide. So we got to times that number by 2. Because what we're really trying to find is 2x, not just x. So we times that by 2, and we get approximately 3.04 times 10 to the minus 3 as our molar concentration for iodide. All right, number trace. It says, what is the molar solubility of silver chloride given the solubility product constant for AgCl being that? So it's again another one of the KSP is going to equal, all right, well, I'm going to get 1 Ag, so it's a concentration of Ag plus to the first power times concentration of chloride ion to the first power as well, because you get 1 of each. So, well, we want to know how much those are. There's some value, x. Concentration of Ag plus is going to equal the concentration of Cl minus, so we get KSP equals x squared, x being the molar solubility. So if we want x, it equals the square root of KSP. So I plug that in, and I get beep bop boop 1.34 times 10 to the minus 5 as my molar solubility for silver chloride. Number 4, concentration of fluoride ions in a saturated solution of barium fluoride is blank. So we know barium fluoride. KSP expression is going to be the concentration of barium ion to the first power, because we get 1 barium, times the fluoride ion concentration squared, because I get 2 fluoride ions. So now I go, all right, well, if I'm dissolving X amount of barium fluoride, I'm going to get X amount of barium, and I'm going to get 2X amount of fluoride ion. So now that X is to the first power, and this 2X is squared. So when we square 2X, we end up with 4X squared. We got X there. So we end up getting the KSP equals 4X cubed. So what we're trying to find is the molar solubility, which is X. Actually, we're not. We're trying to find the fluoride ion concentration. So we're trying to find 2X. So first step is to find X. So we do some algebra, and we get X equals KSP over 4 to the 1/3 power. And we get 7.52 times 10 to the minus 3. And now, well, that's X. I want 2X, so I got to times that by 2. And I get 1.5 times 10 to the minus 2 molar for the fluoride ion concentration, because the fluoride ion concentration is 2X, not just X. And so that is my final answer. Cool. So not too bad, right? See you in class.